Hello, this is Math 1428, Alternative Delivery for 25th March 2020. You should have done a cursory reading of Section 4.4 in order to gain the maximum benefit from this, and I assume that, but please do active working through these slides, hitting the play and pause, and have pencil, paper, calculator, and book. I am going to open with my comment about remaining flexible. We do have challenges in this current crisis, but I'm up to the task, and I think you are too. If you stay with it and work hard, I think we'll find safe harbor. Grades will be earned, and grades will be rendered, and goals can be achieved without delay. So I really encourage you, if possible, to stay with our course. Chapter 4.2 is called Theorems about Zeros of Polynomial Functions. We're going to find a polynomial with specified zeros. Given a polynomial function with integer coefficients, we're supposed to be able to find the rational zeros and the other zeros if possible. Sometimes that'll be easy to do, other times it's so hard it will not be deemed possible. And we'll also talk about a rule called Descartes' rule of sign to find information about the number of real zeros of a function with a polynomial function, rather, with real coefficients. Okay, so here are some examples, and the thing I really want to stress is many of the theorems in this section make substantial use of what type coefficients there are. So here you have complex coefficients. You have I and 2 plus 4i in addition to 5 and minus 3. Now in this next one you just have real coefficients, but they are in a couple cases irrational. The square root of 2 is irrational and pi is irrational. And here you have rational coefficients. Each of these is a rational number. And down here you have integer coefficients. Since the theorems deal with these kinds of numbers, it matters. And so reviewing the definitions of these different sets of numbers would be very useful for you as you go forward. The fundamental theorem of algebra states every polynomial function of degree n, where n is bigger than or equal to 1, has at least one zero in the set of complex numbers. Now the zero might be complex. Although the fundamental theorem guarantees a zero exists, it doesn't tell us how to find it, and that's one of the things we'll be talking about as we go forward in this section. You should then recall that the zeros of a polynomial function allow you to factor it with the zeros. So here C1, C2, and dot 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 through Cn are zeros of the function, and we have a constant being multiplied by that, but that means that C1, C2, and Cn are the zeros of the polynomial. And with the right choice of this, you can come up with the polynomial that you need. So this is how we factor this, and it's not necessarily a unique factoring. So let's talk about how do you find polynomials with given zeros. And here's an example, problem number 3. So based on what we've talked about before, you should find a polynomial of degree 3 with those as numbers. Please press pause, do the problem, and then hit return. We'll see how you did. Let's see how you did. Okay, so what we're going to do is, all we need to do is take those zeros. So this is the factor, x plus 3 corresponding to the 0 minus 3. This is the factor corresponding to the 0 of 2i, and this is the factor corresponding with the 0 of minus 2i. And so what we do is we multiply all these together, and we end up with this as our answer. Now we could have had any coefficient up here, but we just took 1 because that's the simplest number. The problem just asks us to find 1. Here, problem 13 asks us to find a polynomial function of degree 5, and it has minus 1 as a 0 of multiplicity 3, 0 as a 0 of multiplicity 1, and 1 as a 0 of multiplicity 1. Press pause, and let's see how you did. Let's return and see how you did. Okay, so your answer, again, for simplicity, we're going to let that leading coefficient be 1. It actually could be anything. And so we have here is minus 1 is a 0 of multiplicity 3. Here 0 is a multiplicity of 1. There's automatically a 1 there. And 1 is a 0 of multiplicity 1. Again, there's an automatic 1 there. Multiplying everything together, we end up with this being an example. Now, it is possible for there to be non-zeros, and they can be complex conjugates of each other, a plus bi and a minus bi. And in fact, what we're going to have is we're going to have a theorem that tells us that that is often the case. So, if a complex number a plus bi is a 0 of the polynomial function f of x with real coefficients, then its complex conjugate a minus bi is also a 0. It is important that the polynomial have real coefficients for that to be true. And so they give you an example there. If 2 plus 7i is a 0 of a polynomial with real coefficients, then 2 minus 7i must also be a 0. Some students summarize this by saying non-real zeros occur in conjugate pairs, but that doesn't tell you that the polynomial had to have real coefficients, but it must. When a polynomial has rational numbers for coefficients, the same kind of thing is true for irrational zeros. They'll occur in pairs which are conjugate pairs, and that's what this next statement is about. So if a plus c square root of b, where a, b, and c are rational and b is not a perfect square, is a 0 of a polynomial with rational coefficients, then its conjugate a minus c times the square root of b is also a 0. So irrational zeros can occur in conjugate pairs in this situation. Again, it was important that there be rational coefficients. So here are some problems for us to do. Suppose a polynomial function of degree 4 with rational coefficients has the given numbers as zeros. Find the other zeros. We're going to do number 19. So everybody look at number 19, hit pause, and then hit play, and we'll see how you did. Let's see how you did. Since the polynomial of degree 4 can have at most 4 zeros, and since it has rational coefficients, the other zeros are the conjugates of the given zeros. So the two additional zeros are I and 2 plus the square root of 5. Problem 39 says, find a polynomial function of lowest degree with rational coefficients that has the given numbers as sum of its zeros. Now, since this is sum of its zeros, what happens is if 1 minus I is a 0, then 1 plus I has to be 0. And if minus square root of 5 is a 0, then plus square root of 5 has to be 0. Press pause, and do the problem and return and see how you did. Let's see how you did. Okay, so what happens is that we need to find a polynomial that has this and this as sum of its roots. That means that also this is a root, and that's a root, as I said. So you have a constant, and we're going to let that constant be 1 just for simplicity. Then we're going to be multiplying this times this times this times this, because those are all factors. If we do all the multiplications, we get this as our answer. You should take the time to do those multiplications because that will reinforce your algebra skills. We now turn our attention to integer coefficients and a theorem called the rational zeros theorem. This theorem will tell us all the candidate rational zeros, but we still have to test them either by substituting in or by using synthetic division. So here's the rational zeros theorem. So suppose you have a polynomial that is looking like this, where all the coefficients, all the a sub n's are integers. Consider a rational number that is p divided by q, where p and q are relatively prime. meaning they have no common factors besides -1 and 1. If p over q is a 0 of p of x, then p the numerator has to be a factor of a0, and q has to be a factor of the leading coefficient, a sub n. So let's do a problem. For each polynomial function, you want to find the rational zeros and then the other zeros and factor it into linear coefficients. And so problem 55 is here, and what you first have to do is determine all the possible rational zeros and then test them and go from there. So press pause and we'll see how you do. Let's see how you did. Well, the numerator is going to be possible factors of -6. So that can be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now since we have a 1 here, the only possibilities for q are going to be plus or minus 1. So when I look at the combinations of p over q, these are the numbers that I get. And again, the signs can be taken in different order. That gives you the plus and minus possibilities. So we have to test to see if each one of these is a 0 or not. Now, if we substitute them in, that's one way to test. Another way to test is by synthetic division. Let's use synthetic division to test whether 1, 0 is -3. We put -3 in there. -3 was one of our candidates. And we find, yes, it is a 0. And so now we know, and this is going back to chapter 4.3, that the function we started out with has x plus 3 as a factor, and what is left is, this is now an x squared term, this is x squared. There is no x, but it is x squared minus 2. So we now have a quadratic that we can solve. We know how to do that many ways from earlier chapters. We find x is plus or minus 2. So there's only one rational 0 minus 3, but the other zeros are plus or minus 2. You found all three of them already. And part B said write it in factors forms. And so what we're doing is we're saying, oh, if -3 and plus and minus root 2 are zeros, then we can write it like this. A similar kind of problem, same directions, for problem 61 shown here. But now you have a 27 as the constant term, and you have a 2. Press pause, do the problem, and come back, and we'll look at the solution. Well, the possibilities for p are how many divisors do we have of 27, and these are the divisors of 27. Now here we have a 2, so the possibilities for the denominator would be plus or minus 1 and plus or minus 2. Now we get a lot of possibilities when we look at pairing all these things up, including the SIGNs, the signs, but these are all possible rational roots, and we have to check them all until we find a root. Now we can use synthetic division, and if we check if -3/2, which is right here, is a root, we can divide that and find out that yes, it is, because I get a 0 here. And that means what I'm left with is 2x squared plus 18. So the function can be factored as x plus 3/2 times 2x squared plus 18. And so this is what I can multiply together and say that this is the expression that I get. This one I just factored the 2 out of the 2x squared plus 18. So now we can look at the roots, and you see we knew this root was -3/2, but this factor will set it equal to 0. We get roots that are plus or minus 3i. And so that means the only rational 0 is -3/2. The other two zeros are plus or minus 3. It can only have 3 because it's a cubic, and so the answer to the problem is this factor. That's part B. The last topic we're going to cover in this section is called Descartes' rule of sign, and it is important that you realize it's in the theorem, but you have to maybe emphasize it. We must have the polynomial arranged in descending order or ascending order, and no zero term is written and no zero terms written in the constant term is not 0. We're going to count what we call the variation of signs, and that's going to help us know about how many roots of the polynomial are possible. So here is an example, and I'm just using this example from your book. I usually don't use examples from your book. I leave those for you to read. This time I'm talking about it because I think it's a particularly nice example. So what we need to do before we do this theorem is we need to know how to count variations in sign for the polynomial and what happens when we put minus x in for x. So here is the polynomial, and we're counting how does it vary in signs. We're counting the number of variations in sign. So here we go from positive to negative, that is one variation in sign. Here we go from negative to positive, that's the second variation in sign, and that's the last variation in sign. So the number of variations of sign is 2. Now, if we put minus x in for x and simplify, this is what we get. Note that this is significantly different than p of x in this case. So now we're going to see how many variations in sign, but we see that we start out minus, don't change, and finally change to positive. So there's one variation in sign. So now we go from minus x to 4. So what that means is there's one variation in sign. Now I'm going to quote Descartes' rule of sign. So suppose you have p of x written in descending or ascending order, be a polynomial with real coefficients and a non-zero constant term. If there is a zero constant term, you factor the x out first, and we'll have an example like that. The number of positive zeros is either the same as the number of variations of sign in p of x, or less than that number by a positive even integer until you get down to 0. The number of negative real roots of p of x is either the same as the number of variations of sign of p of minus x, or is less than that number of variations in sign by a positive even integer. A zero of multiplicity m must be counted m times. Alright, so here is a problem. We want to say, what does this Descartes' rule of sign tell you about the number of positive real zeros and the number of negative real zeros for this function? Press pause, do the problem, and then we'll return. Let's see how you did. Okay, so there are 3 variations in sign for r of x. So there are 3, or reducing it by an even positive integer, 1 positive real zeros. Whenever we substitute minus x, we get this. There is only one variation in sign in r of minus x, so there is one negative real zero. Let's do another one. This is problem 81 in your text. Press pause, do the problem, and then return. The number of variations in sign of f of x is 3. So that means the number of real zeros, positive real zeros, is either 3 or 1. When we look at f of minus x, we get this expression down here, and you see there are no variations in sign, so there are 0 negative real zeros. Let's do another one. What does Descartes' rule of sign tell you about the number of positive real zeros and the number of negative real zeros of this function? Now, what you should do is factor out, because we have a 0 constant term, you should factor the x out first, say x is 0, and then concentrate on the other. Press pause, do the problem, let's see how you did. Let's now see how you did. Okay. Now, what we did is that when we there's one variation in sign of r of x, and they really should have factored that out, but you still have 1. So there's one positive real 0 and there's one negative real 0, but x equals 0 is also a root. Now more than ever, time is precious. Each day must count. Do the math, it will make you strong. See you on Friday.